Okay, I want you to answer these questions after you put your playback on pause, and then I'll come back and discuss the answer with you. First, which would have higher entropy, water at 45 degrees Celsius or water at 65 degrees Celsius? And second, would solid water or ice at 0 degrees have a higher entropy, or would liquid water at 0 degrees Celsius have a higher entropy? Okay, so water at 45 versus water at 65. When the temperature increases, entropy increases. So B would have the higher entropy. And for 2, liquid water is going to be at a higher entropic state than ice or solid water. Would entropy increase or decrease when solid sodium chloride dissolves in water, becomes aqueous sodium chloride? And when carbon dioxide gas dissolves in water and becomes aqueous carbon dioxide? When sodium chloride dissolves and becomes aqueous sodium chloride, entropy increases. However, when carbon dioxide gas dissolves, the entropy state of aqueous carbon dioxide is actually lower. That's because gases have so many degrees of freedom that it's a loss of entropy when they dissolve in a liquid. Okay, which would have higher entropy? Methane CH4, ethane C2H6, or propane C3H8? And in 2, N2O4 or NO2 or NO, which would have higher entropy? Well, remember, generally the higher the molar mass and the more complex the molecule is, compounds like that are going to have more degrees of freedoms and energy can be dispersed over a greater area than in simpler molecules. So for number 1, it'd be the propane C3H8, and for 2, it'd be the N2O4. So in number 4, in the following reactions, predict if entropy is increasing or decreasing. So the first one is butene, C4H8, turning into 2 molecules of ethane, C2H4. While it's tempting to say it's the C4H8 because the molecule is more complex, it's completely overridden by the fact that you get twice as many moles of gaseous molecules after it decomposes into ethane. So the answer would be an entropy increase because more moles of this gaseous ethene are being produced. In 2, we have carbon dioxide gas going to carbon dioxide solid. That's kind of a duh. Of course, entropy is going to decrease in that situation. In 3, we have carbon dioxide as a gas at 273 going to carbon dioxide as a gas at 305. Whenever you heat a substance and there's no phase change, then the entropy is going to increase for that system. And for 4, we have nitrogen gas and 3 moles of hydrogen gas going to 2 moles of ammonia. That's going to be an entropy decrease because the total number of moles of gas is decreasing. So now let's calculate the entropy of a reaction. 4 moles of ammonia plus 5 moles of oxygen yield 4 moles of nitric oxide and 6 moles of water. But first, predict. Let's predict. Will the delta S, the change in entropy for this reaction, be positive or negative? And just take a look here. You've got 4 and 5, 9 gaseous moles on the reagent side, and 4 and 6, 10 gaseous moles on the product side. So you have more gaseous moles on the product side being formed as a result of the reaction. That is an increase in entropy. All right, let's go about now the process of calculating the change in entropy from the standard entropy values in this table for ammonia, oxygen, nitric oxide, and water. Turn your playback off. Try and do this calculation and see if you can come up with the change in entropy. Okay, here we go. We're given, of course, the standard entropies. We're going to find the change in entropy, and the relationship is going to be that the change in entropy equals the sum of the entropies of the products minus the sum of the entropies of the reagents. Remembering that entropy is given in joules per mole K, And therefore, if we have 4 moles of ammonia, we have to multiply 4 by the 192.8, because that's for 1 mole, and we have 4 moles of it, etc. for the other elements. So here's the calculation. Did you get it? It's 178.8 joules per Kelvin. Now let's consider the effect of enthalpy and entropy on a change being spontaneous or non-spontaneous. A change in which heat is absorbed we call endothermic, with a positive delta H, or positive change in enthalpy value, and it pushes the change to be non-spontaneous. But a change in which heat is released we call exothermic, with a negative delta H value, and that pushes the change to be spontaneous. Now, what about entropy? A change in which a system becomes more organized or ordered is a change in which entropy decreases with a negative delta S, and it pushes the change to be non-spontaneous. And vice versa, if a change in which a system becomes more disordered is a change in which entropy increases and pushes the change to be spontaneous. So if the change is exothermic and the entropy increases, that's going to be a spontaneous change. And if the change is endothermic and entropy decreases, both of these are fighting against a spontaneous change, the change will be non-spontaneous. However, if the two go in different directions, if the enthalpy is exothermic, but the entropy change decreases, in other words, the enthalpy is pushing the change to be spontaneous, and entropy is pushing the change to be non-spontaneous, then temperature is going to be the deciding factor. And the same thing is if the change is endothermic and entropy increases. They're fighting against each other, with enthalpy saying no, not spontaneous, and entropy change saying yes, spontaneous. That also is going to be dependent upon temperature. As examples, let's look at the following processes. A bomb explodes. Is that endo or exothermic? Pretty darn exothermic. And is the change in enthalpy positive or negative? That will be a negative change in enthalpy. Is the change towards order or disorder? Very definitely toward disorder. So the change in entropy, is it positive or negative? It's going to be decidedly positive. This will be a spontaneous change. Now what about ice melting? Clearly that's an endothermic process. Heat is being absorbed and the enthalpy is positive. But as ice melts, water's breaking away from the ice crystal lattice and becoming more disordered. So the entropy is increasing. And as we know, ice melts when the temperature is above 0 degrees Celsius. It is a temperature-dependent change. What about steam condensing? That's very exothermic. If you've ever burned yourself reaching for a piece of steamed broccoli in the steamer with a negative change in enthalpy. But when the steam condenses from the gaseous state to the liquid state, that's a change towards order with a negative entropy value. That too is temperature dependent. So steam condensing is a temperature dependent process. And finally, how about carbon dioxide and water forming methane and oxygen? Is that going to be spontaneous or non-spontaneous? Well, this is an endothermic process. Heat is being absorbed in this process, and the entropy change is negative. This is a non-spontaneous process. We're used to seeing methane and oxygen burning to form carbon dioxide and water, not the reverse with carbon dioxide and water reacting to form methane and oxygen. So let's review this a bit. Spontaneous processes are favored in exothermic processes in which the sign of the enthalpy is negative. For a process to be spontaneous, the entropy of the universe must increase. If the above are true, then what is the connection between entropy and enthalpy? A reaction that is exothermic is releasing heat to the surroundings. And what does that do? Increase or decrease the entropy of the surroundings? Of course, it increases the entropy of the surroundings. Therefore, the delta S the change in entropy of the surroundings is proportional to the heat evolved by the system. The heat evolved by the system in an exothermic change, or the heat that's absorbed by the system in an endothermic change, has an effect on the entropy of the surroundings. Therefore, the change in entropy of the surroundings is proportional to the heat evolved or absorbed by the system. Now, why is this negative sign there? Well, that's because if heat is absorbed by the system, Q is going to be positive, and the change in entropy of the surroundings is going to be negative. So negative times positive is a negative, and it maintains its proportionality. Whereas if the heat is being evolved by the system, released into the surroundings, that's going to be a negative Q, and we put the negative sign there so that a negative times a negative is a positive, because that will have a positive effect on the change in entropy of the surroundings. Now, there's another factor. Suppose I'm walking down the street and I see a homeless person, and I give the homeless person $5. All right? And then I walk a little further down the street and I come across Bill Gates, and I give him $5. So my question to you is, whose life has been more impacted by my donation, the homeless person or Bill Gates? And of course, it's the homeless person, because he doesn't have any money, and giving him $5 is a big deal. Whereas for Bill Gates, he'd probably turn around and give it to the homeless person as well, right? So, the effect of temperature on entropy is a factor. The change in entropy of the surroundings is greater at lower temperature. Therefore, the delta S of the surroundings is also proportional to the inverse of the temperature. And if we combine this, we get that the delta S of the surroundings is equal to the negative of the heat evolved by the system divided by the temperature. And if this is occurring at constant pressure, then the heat of the system is equal to the change in enthalpy of the system. So the bottom line is that the change in entropy of the surroundings is equal to minus the delta H, the change in enthalpy of the system, divided by the temperature. When a system process is exothermic, it adds heat to the surroundings, increasing the entropy of the surroundings. And when a system process is endothermic, it takes heat from the surroundings, decreasing the entropy of the surroundings. The amount of change of the surroundings entropy depends upon the temperature it is at originally. So here we have a question for you to try. For the reaction at 25 degrees, we have nitrogen plus 3 moles of hydrogen forming 2 moles of ammonia. And the change in entropy of this system is minus 197 joules per K. Why is that? Because you're decreasing the number of gaseous moles in this reaction. So it's going to have a negative entropy. Calculate the change in enthalpy in the system in kilojoules if the enthalpy of formation of ammonia is minus 45.9 kilojoules per mole. Choose A, B, C, or D. Turn your playback off, calculate it, and come back. Okay, here we go. Here's the reaction, and we'll set it up putting the standard enthalpy values underneath each appropriate reagent. Any element in its stable elemental form is going to have 0 enthalpy, and the enthalpy of formation is the heat of this reaction forming ammonia. So to calculate the enthalpy of the system, it's the sum of the enthalpy of the products minus the sum of the enthalpy of the reagents. Therefore, the change in enthalpy of the system is 2, because we have 2 moles of ammonia. 2 moles times its enthalpy of formation minus 45.9 kilojoules per mole. And that equals minus 91.8 kilojoules. So here's a question for you. For the reaction at 25 degrees Celsius of nitrogen gas plus 3 moles of hydrogen gas yields 2 moles of ammonia gas, the change in entropy of the system is minus 197 joules per Kelvin, and the enthalpy of the system is minus 91.8 kilojoules. So calculate the change in entropy of the surroundings at 298 with this formula. The change in entropy of the surroundings is equal to minus the enthalpy of the system divided by the absolute temperature. Which one of these is it going to be? Turn your playback off, do it, and then come back for the answer. All right, here we go. It's really a matter of just plugging in and remembering that you have a negative times a negative, which is a positive. So you're going to end up with plus 0.308 kilojoules, which is 308 joules. So the second part of this question, is this reaction spontaneous at 298 Kelvin? Do your calculation and then come back. We'll discuss the answer. Okay, here we go. All we have to do is figure out the change in entropy of the universe. And if that's positive, then it's going to be a spontaneous change. And we have two components of that, the change in entropy of the surroundings plus the change in entropy of the system. The change in entropy of the surroundings is positive 308 joules. The change in entropy of the system is minus 197 joules. Add them together, you get a positive 111 joules. So the change in entropy of the universe is positive, so yes, this is a spontaneous change. Let's do another one. Here's a combustion reaction of propane with oxygen to form carbon dioxide and water. And the enthalpy of the reaction is, as you might expect, a burning propane gas, very exothermic, minus 2044 kilojoules at 25 degrees C. So that's going to have a sizable effect on the entropy of the surroundings, which is what this question wants you to calculate. You're heating up the surroundings. The entropy of the surroundings is going to increase. What is that increase in entropy? Why don't you turn your playback off, do it, and then come back, we'll show you. All right, given that the enthalpy of the system is minus 2044 kilojoules, the temperature is 298 Kelvin, we need to find the change in entropy of the surroundings in joules per Kelvin. The equation is the change in entropy of the surroundings is equal to minus the change in enthalpy of the system divided by the absolute temperature. So our solution, after plugging in the minus 2044 kilojoules for the enthalpy of the reaction, dividing it by 298 Kelvin, we get a change in entropy of the surroundings of 6.86 times 10 to the 3 joules per Kelvin. And this is an answer that makes sense because combustion is largely exothermic, so the entropy of the surroundings should increase significantly. So now we're going to talk about Gibbs free energy, delta G. It's defined as the maximum amount of energy from the system available to do work on the surroundings. And it's given the formula that the change in free energy of the system is equal to the change in enthalpy of the system minus the absolute temperature times the change in entropy of the system. It is a state function. As a state function, it only considers the free energy of the products and the free energy of the reactants, not the path used to get from one to the other. So to calculate the change in free energy of the reaction, it's the sum of the free energies of the products minus the sum of free energies of the reactants. Now when delta G is less than 0, in other words, when it's negative, there's a decrease in free energy of the system that is released into the surroundings. Therefore, a process will be spontaneous when delta G is negative. So the useful guide is a negative delta G, it's a spontaneous process. A positive delta G, it's not spontaneous. And if delta G equals 0, the system is at equilibrium. Now we're going to examine 4 scenarios in which we changed the enthalpy and the entropy and how the corresponding signs of those changes of enthalpy and entropy affect the sign of the change in free energy. Suppose we have an exothermic change where the system becomes more disordered. The sign of the enthalpy change is going to be negative in an exothermic change, and the change in entropy is going to become positive if the system becomes more disordered. So both the enthalpy term is negative and the temperature times the change in entropy is negative. So delta G is always going to be negative in this scenario, and therefore it's going to be a spontaneous change because when the free energy is negative, it's a spontaneous change. Now, what about a system where you have an exothermic event, but the system becomes more organized or more ordered? In that scenario, the enthalpy is negative, but the sign of the entropy change is also negative. A negative times a negative is a positive, so this whole term becomes positive, working against a spontaneous change, whereas the enthalpy term is negative. So the deciding factor in this scenario is going to be the magnitude of the absolute temperature. The bigger the absolute temperature, the bigger this whole positive term becomes. So it's not going to be spontaneous at higher temperature, but it is going to be spontaneous at lower temperature, because then the negative enthalpy term will be greater than the positive entropy contribution. And the sign of delta G will be negative, spontaneous, at lower temperature. Now, what about just the reverse, an endothermic process and the system becoming more disordered? In that event, the sign of the enthalpy change is going to be positive, and the sign of the entropy change is also going to be positive. So the enthalpy term is working against a spontaneous change by being positive, but this is a minus times a plus, so this term is going to be negative, and at higher temperature it will be a larger value than the enthalpy term, and therefore cause the free energy change to be negative at higher temperature. So this is going to be spontaneous at higher temperature when you have an endothermic event, but the system becomes more disordered. And finally, there's an endothermic event and the system becomes more ordered. In that scenario, both the enthalpy change is working against a spontaneous change, and so is the entropy change, because it is minus by becoming more ordered, and a minus times a minus is a plus, so this whole term is positive too. So no matter what you do at what temperature, delta G is going to be positive, and it's not going to be spontaneous. A very endothermic reaction occurs when we mix barium hydroxide and ammonium nitrate. First we combine these two solid reactants, and then we stir, and we notice that the flask begins to get colder and colder and colder. We can track the temperature with a thermometer. We squirt a little water on a board, and then we set the flask down, and after a few seconds, just a few seconds, the water freezes and the board is able to be lifted up when the flask is lifted up. So here's the reaction that we just watched. Barium hydroxide with 8 waters of hydration is a solid. We mix it with ammonium nitrate, which is a solid, and we get out of that dissolved barium ion and dissolved nitrate ion and dissolved ammonia and 10 moles of liquid water. So the first question is this reaction endothermic or exothermic? I think it's safe to say it's a pretty endothermic reaction, what with the water freezing and all. Secondly, is entropy increasing or decreasing? Well, look at this. We have a solid form here and a solid form here in the reactants, and we don't have any solid in the products. We have aqueous barium and aqueous nitrate and aqueous ammonia and 10 moles of liquid water. So it's pretty clear that entropy is wildly increasing. The system is becoming way more entropic. So, is this reaction, would it become non-spontaneous at some higher temperature or at some lower temperature? Which one, higher or lower? And again, we have to take a look at the free energy equation. We know that the reaction is very endothermic, so is a big plus on the delta H. And we know that the entropy is increasing, so it's a big positive on the delta S. For a reaction to be spontaneous, delta G has to be negative. And the negative part of this equation is this part with the absolute temperature times the change in entropy. So if the temperature is high enough, this whole term is going to be a negative, and if it is greater in magnitude than the positive enthalpy, then delta G will be negative. Therefore, if the temperature is lower than that threshold, the magnitude of this part of the equation will be less than the positive enthalpy, and delta G will be positive and non-spontaneous. So this is going to be non-spontaneous at a lower temperature. So let's try this one. The reaction of carbon tetrachloride in the gaseous form yields carbon as a solid plus 2 moles of chlorine gas as a gas, has a change in enthalpy of plus 95.7 kilojoules and a change of entropy of plus 142.2 joules per Kelvin. And it wants us to calculate the minimum temperature in which this reaction will be spontaneous. So here's our given information. We have to find the temperature above which the reaction is spontaneous. And we're going to be using the free energy reaction delta G equals delta H minus T delta S to come up with a solution to this. For the reaction to be spontaneous, delta G has to be a negative value, or this term delta H minus T delta S has to come out negative, has to be less than 0. Well, the delta H is a positive value, so that means the T delta S term in magnitude has to be greater, so that when you subtract it, the whole value for the whole thing is going to be less than 0 or a negative value. So you're looking for T. You're going to solve this equation for T, the temperature above which the reaction will be spontaneous. So you just divide the 95.7 times 10 to the 3 joules. That's the change in enthalpy. Quick note, remember to convert from kilojoules to joules so that the enthalpy and the entropy are using the same units. Enthalpy is usually given as kilojoules and entropy as joules. So you have to convert either the enthalpy to joules or the entropy to kilojoules, but they have to be on the same page. Anyway, solve this and you get a temperature of 673 and above. Temperature must be higher than 673 Kelvin for the reaction to be spontaneous. Now let's learn how to calculate delta G. At 25 degrees, it's pretty simple. You go to the table and you look up free energies at 25 degrees Celsius, and that'll be per mole. So you take the number of moles of a given product times the free energy from the table and any others. You add those all up. That's the sum of the free energy of the products, and you subtract that from that the sum of the free energies of the reactants. That'll give you the free energy change of the reaction at 25 degrees. If you're not at 25 degrees, you can assume that the changes in enthalpy and entropy are negligible at temperatures other than 25 degrees. So you can calculate the free energy change at a temperature other than 25 degrees by using the free energy equation delta H minus T delta S. Calculate your delta H and delta S from the tables at 25 degrees. It's not going to be at 25 degrees, but the values of delta H and delta S aren't going to change that much. The temperature is going to change, and you'll get a pretty good approximation of what the free energy is going to be at that different temperature. Okay, let's see if you can calculate the free energy change at 25 degrees for the reaction of methane and oxygen forming carbon dioxide, water, and ozone. Turn your playback off, try it, and then come back. We'll discuss the answer. So now let's calculate the change in free energy at 25 degrees for the reaction of methane reacting with 8 moles of oxygen to form carbon dioxide, 2 moles of water, and 4 moles of ozone. And we're given the table of standard free energy changes in terms of kilojoules per mole. So from this table and from the notion that you are going to use the sum of the free energies of the products and subtract from that the sum of the free energy of the reagents to get the free energy change for the reaction. So here we go. We start with the product side, change in free energy of carbon dioxide. It's 1 mole, so we take it right from the table, minus 394.4 kilojoules. And we add to that the free energy of water, minus 228.6 kilojoules, times 2, because we have 2 moles of it. And we add to that the free energy change of the ozone, but we have 4 moles of the ozone, so it's 4 times the standard free energy of ozone, 163.2. So that is the sum of the free energies of the products. We subtract from that the sum of the free energies of the reagents. Oxygen is 0, so we don't have to bother with it, but methane is minus 50.5 kilojoules. And of course we're subtracting that value of the reagents from the products. And when all is said and done, we have minus 148.3 kilojoules as our answer. Did you get it? The reaction of sulfur dioxide plus a half a mole of oxygen yields sulfur trioxide. It has a change in enthalpy of minus 98.9 kilojoules and a change of entropy of minus 94 joules per Kelvin at 25 degrees C. Calculate the estimated free energy change at 125 degrees Celsius and determine if it is spontaneous. So what you need to know to calculate this is that the change in enthalpy and the change of entropy at temperatures other than 25 degrees Celsius are not that much different than those values at 25 degrees Celsius. So you can use the values you determine for the change in entropy and enthalpy that you find in the tables and just change the temperature in the free energy equation to the desired temperature. Turn your playback off, see if you can calculate this, then we'll show you the answer. Here's our free energy reaction. We enter the enthalpy change. We calculate the new Kelvin temperature, 273 plus 125, and we multiply it by the change in entropy, correcting for the fact that entropy must be displayed as kilojoules and not joules to match the units of enthalpy, which is kilojoules. So the free energy change of the reaction is minus 61.5 kilojoules. And because the change in free energy is a negative value, this is a spontaneous reaction. Now, to estimate an equilibrium temperature, which is the crossover temperature between a spontaneous and non-spontaneous change, use the free energy equation set to equal 0. That's the equilibrium point. So let's try this one. The temperature at which the following process reaches equilibrium at 1 atmosphere is the normal boiling point of the hypothetical compound XD. XD is a liquid in equilibrium with XD as a gas. That's the boiling point when they're in equilibrium. Use the following thermodynamic information to approximate this temperature in degrees Celsius. Watch your units. So here are the change in enthalpy values and the change in entropy values, both for XD in the liquid state and XD in the gaseous state. Pause your playback, try to do this problem, then come back and we'll discuss it. All right, here we go. First of all, we calculate the change in enthalpy, products minus reactants, so it's minus 134.3 kilojoules, minus a minus 157.9 kilojoules for the liquid state, so the change in enthalpy is plus 23.6 kilojoules. The change in entropy is 0.2827, that's after converting joules into kilojoules, keep the units consistent, minus 0.1496 kilojoules, and that's a change in entropy of 0.1331 kilojoules. So delta H minus T delta S equals 0, the equilibrium point, and we plug in the change in enthalpy and the change of entropy, and we solve for temperature. And the temperature comes out to be 177 Kelvin. And if we subtract that from 273, we convert it into degrees Celsius, 95.6. Did you get it?